spectral evolution is one of the most interesting properties of gamma ray bursts. And there are two methods of analysis. The first one is a spectrum analysis. So you build spectra in different time intervals and look at the spectra. And the key parameter which describes spectral evolution is, for example, a peak, the peak in the new spectrum. And usually the spectrum evolves from hard to soft. So the peak goes down. Okay. So another type of analysis is the analysis of light curves. You build light curves in different energy bands and make a cross-correlation analysis. This analysis is also called spectral lag analysis. In this analysis, you measure the time delay between light curves in different energy bands. I forgot to say that this is the energy time diagram of gamma ray burst of 4, 12, 12. This is the time, this is the energy, so this is a burst. And the spectral evolution is clearly seen. This is light curve of this burst. We used in our analysis the second method, which uses spectral lag. So the traditional method of spectral lag analysis is based on calculation of spectral lag between light curves in two different energy bands. And these energy bands are usually very wide. For example, the channels of Batzy experiment. And on this picture, you can see the light curve of one of the bursts registered by Batzy in 4 channels and corresponding cross-correlation function between the first, the softest channel, and the third channel, this one. And you see that it's shaped very smooth. This situation is very rare because light curves of gamma bursts are very complex, and this is the ideal situation. And the maximum of this curve can say us about time delay between time profiles. But usually some people use only one value of spectral lag, the lag between the third and the first channel. But you can calculate 3 values because we have 4 channels. In this case, we can only get a view of general behavior. But we decided to modify this method to see some details of spectral evolution. The basics of the method is the same. It's cross-correlation analysis, but we use very narrow energy bands. And a number and the width of energy channels depend only on gamma ray burst properties, and they are not fixed. In the brightest events, we used more than 20 channels. So using this method, you can investigate spectral evolution in more detail. We use data obtained by E.B. Sisgry and SPI experiments on Bott integral. You heard today many details of these experiments, and I say just a few words about it. So the SPI experiment is a spectrometer which consists of 19 germanium detectors, and its energy range from 20 keV up to 8 MeV, and it's presented here. Its spectral evolution was very good. And The second experiment is EV-SysGrid experiment, which energy range is more softer, and it registers photons effectively up to 200 keV. We analyzed gamma ray bursts from our transients catalog of SPI experiment and selected 28 most intense bursts. 6 bursts have a very complex multi-pulse structure. One of these bursts is presented here. This is the 08, 07, 23 burst, and you see that it consists of at least 6 components. And we investigated each component independently for such events. So total number of investigated events is 43. The brightest events were analyzed using SPI data, because the effective area of SPI experiment is not so good as ISGRI. So bursts with medium intensity were analyzed by using ISGRI data. Okay, so the algorithm of analysis consists of next steps. The first one is building energy time diagram and visual analysis of properties of bursts, such as intensity, duration, hardness of spectrum, etc. The next step is building a light curve in wide energy band and pulse resolving procedure. We use exponential pulses of firstly used by Norris. So this is formula. The next step is the forming of light curves in narrow energy channels with high temporal resolution, and the cross-correlation analysis of light curves. We calculated spectral lag between the first, the softest channel, and the others. And then we fitted dependence of spectral lag energy. Results. On this picture, you can see the dependence of spectral lag on energy channel for gamma ray burst 050525 and 040323. You see that the dependence has very simple logarithmic law, and such behavior was observed in 85% of cases. We used this formula to fit this curve. But in 15% of cases, we observed some break in the relation. And we see that the simple logarithmic law does not fit this curve. And we used two logarithmic law function is the sum of two logarithmic law with exponential break. So the new parameter which characterizes spectral evolution is this A parameter. We called it spectral lag index. The absolute value of this parameter characterizes the speed or intensity of spectral evolution. So the bigger value, the faster spectrum evolves. The sign of this parameter characterizes the type of spectral evolution. So if it's positive, we observe spectrum evolution from hard to soft. There is some very simple kinematic model which describes spectrum evolution from hard to soft. It's based on relativistically expanding shell. We detect firstly the hard on-axis photons, and then off-axis photons with some delay, and they are softer. We found that break in the relation and negative lag may appear due to complex structure of bursts. So, for example, this is a burst of 505 or 4. This is the energy time diagram. This is light curve and the spectral lag energy curve. We see that this burst consists only one pulse, simple structure. And in this case, we see the simple curve. And if we see the light curve of burst or 3, 12, or 3, we see that it consists of many pulses, at least 5. And in this case, we see the break. Or in other cases, we can see negatively. It's interesting that this burst was analyzed by Nakar. It's a low luminosity burst, and he told us that it's a simple structure burst, but it isn't. Okay.
What's the difference between presenting the data like that and just presenting the peak energy as a function of time?
These are two different methods, but the same. Okay, they are equal.
So you expect to see the peak energy. What?
The peak is model dependent. This is model independent.
Because you say because we don't know where the peak is,
Yeah.
but with BATSI, because this is Swift. Okay.
So the main idea is that you should analyze the burst with simple structure, or you can get wrong results, such as negative lag or zero lag, etc. And we selected events with simple structure and built this diagram. This is a spectral lag index. And this is the duration of the pulse. This is in the sample there is one short burst, and there are 2 episodes of one burst. And you see there is a correlation. So the spectral lag index depends on the duration of the pulse. So you can use this curve to test for example, if you had a light curve of long burst, you made a spectral lag analysis and you get zero lag or negative lag, you may say that this burst consists of several overlapping pulses using this diagram. So if you had long burst and zero lag, it will be here. And you can say that it's not consistent with this correlation, and it consists of several pulses, and it has complex structure.
So this is a pulse, this is the duration of single pulses?
Yes.
So you're saying that if we're off the chart, then it means that we just need to do a better time separation of the pulses, and then we'll be back on this chart?
Yes. Okay. Some test. So it's interesting that a short duration burst does not violate this correlation. Sometimes, often, in a spectral lag analysis of short burst, you can get zero lag or negative lag. And we analyzed them and saw that they consist of several pulses which are overlapping. And this zero lag or negative lag may appear due to different spectral parameters of different pulses. So you should analyze them individually, these pulses of one burst. So the main results of the first part, we modified the traditional method of spectral lac analysis and analyzed 28 bursts registered by SPI and ABC experiments. And we found that for simple structure bursts and for well-separated pulses of bursts, the dependence of spectral lac on energy band is described by a simple logarithmic function law, logarithmic function. The spectral lac index is a new parameter characterizing spectral evolution. And we found the correlation between spectral lac index and the duration of the pulses. So the next part of my talk is to the dichotomy of short gamma bursts. As you know, there are two types of gamma bursts: short hard bursts and long bursts. But in different experiments, they were found that some short bursts are not the short. So there is a first component, which are usual soft burst hard with zero spectral lag. And there is another component, long and softer, which called extended emission. So it was detected in CONUS, BETSI, SWIFT, SPICS experiments. So it's not instrumentation effect. This is light curves of gamma burst 06, 0221 and 03, 12, 14 registered by SPICS. And there is the IPC, or initial pulse complex, so the first part, short part of the burst. And this is the extended emission component. So the duration of it is 50 seconds. Okay, so extended emission of this burst was also found in CONUS experiment. It's interesting that the extended emission component of this burst was detected in high energy band above 100 keV, because all previous detection was in a much softer channel, below 100 keV. Oh, this is, for example, the most famous event, the JB 060614. The light curve of that. So there is a dichotomy problem. We don't know if the extended emission is a common property of all short gamma bursts, or it's a property of another type of the burst. An attempt to solve this problem was done in paper of Norris. In this paper, they investigated 53 short gamma bursts registered by SWIFT, and they found extended emission component in 25% of cases. So in this picture you can see the APC peak intensity and the extended emission component intensity. This is a burst with extended emission, and these are the bursts, usual short bursts without extended emission component. So you see that in this range there is no one burst, and it looks like strange. So the Norris made some simulations, and he suggested that SWIFT can detect bursts in this range, and the simulation showed that SWIFT could detect extended emission in a half of cases instead of 25%. So Norris thinks that it means that short gamma bursts with extended emission are from another burst type population. But extended emission was found also in average light curves in different experiments. In average light curves of short gamma burst without extended emission. So, for example, this light curve, which obtained in Butts experiment, and there is the extended emission component. Initial pulse complex is not presented here. It's there. So we see that some bursts of the sample have extended emission, or it may be evidence that all short gamma ray bursts have extended emission component, but its intensity very low, and we can detect it only if we stacked these events. But on this picture, you can see the average light curve obtained by Norris, and there is no extended emission component. So the question is still open. It's unknown. Is extended emission is a common property of all gamma ray bursts, or it's a property of another burst type? We analyzed gamma ray bursts registered by SPI-CS experiment in energy range above 80 keV. We analyzed 200 confirmed short gamma ray bursts from paper of Savchenko Vladimir and from our catalog, and found extended emission component with significance of 3.5 sigma. We also analyzed unconfirmed gamma ray burst from paper of Rao, and also found some extended emission component. But there are two possible explanations of this behavior. The first one is if extended emission is a common property of all gamma ray bursts, so it means that in this sample we have a real gamma ray burst with extended emission. Or the second, if these events are not real, for example, it may be interaction with energy particles, and this effect is the instrumentation effect. I could say, I must say that confirmed burst is the burst which was registered by at least 2 different experiments. So it is a real confirmed burst. And unconfirmed burst is a burst which registered only in 1 experiment. So its nature is not confirmed. It may be some variation of background, for example. Okay, a few words about theoretical models of extended emission. If you want some details, please read these papers. I say that in the first model was proposed by Metzger. In this model, magnetar is formed after merging, and its relativistic outflow generates extended emission. So in this model, short gamma ray bursts with extended emission are from another burst population. So it doesn't contradict dichotomy. The second model was developed by Lazati group, and in this model, short gamma ray bursts with extended emission are the long gamma ray bursts observed at large angles with jet axis. So it also doesn't contradict dichotomy. And the third model was proposed by Barkov and Pozanenko. You heard the talk about it. So in this model, 2 jets are formed after merging, and neutrino heating jet wide angle is IPC complex, and Blandford-Znaick jet degenerates extended emission component. So in this model, all short gamma ray bursts have the same nature. So
Comment on the second one.
okay.
So I don't think it coincides with any observational constraint that we have on short duration.
Only
gamma.
detection of supernova can.
Not only the supernova, the galaxy where they are observed, the fact that you see the short hard peak. Why would you see short hard peak in long observational angles? The regions where they are observed in non-star formation grid, like it doesn't coincide with any observational constraint that I know of. I may be wrong, but this is how I see it.
I think it's true. You may be moving shorts into longer, but the other way around
Yeah.
is almost
Yeah.
impossible.
Statistics is too low to say something definite.
Yeah, but I think for the extended emission, we do have several that are localized already, right?
Not several, 2 or 3.
Okay, and all the ones that we have localized are not consistent with any star formation.
I would not say so.
Yeah.
So why one need to have statistics at least 10?
Yeah, okay, but so
let's
far,
wait and see.
yeah, okay.
Okay. So the conclusions. The extended emission component was found in light curves of individual short gamma ray bursts and in light curve of stacked events. It significantly complicates the phenomenological classification of gamma ray bursts. There are several theoretical models describing extended emission component, and the question is still open. Is the extended emission a common property of all gamma ray bursts, or it's a property of another population? Okay.
Okay.
Thank you.